Have you ever stopped to think how these massive AI models we use every day actually learn to understand what we really want?
Yeah, it's not just about facts, is it?
Not at all. It's about, nuance, preference, even things like taste.
Hmm.
So today, we're doing a deep dive into something called reward models. Think of them as this hidden compass guiding AI towards what humans actually prefer.
And we're going to be digging into some really groundbreaking research from Skywork AI, their paper, Skywork-Reward-V2, Scaling Preference Data Curation via Human AI Synergy, gives us a fantastic window into this.
Right. So our mission today is to unpack why these reward models are so critical.
Exactly. And look at the big challenges they've faced up till now.
And how this Skywork AI approach, this human AI synergy thing, seems to be setting a totally new standard.
Yeah, really pushing the boundaries on aligning AI with what we humans actually value.
Think of this as your shortcut, folks. We're cutting through the jargon to understand a core piece of AI development, how we make AI helpful, and crucially, harmless.
You should walk away with some real aha moments about how human smarts and AI scale are being combined. It's pretty profound stuff.
Okay, let's dive in. So first things first, what are reward models? Why do we need this compass in the first place?
Okay, so reward models, RMs for short, are really key components in reinforcement learning from human feedback. RLHF.
Right, RLHF, we hear that acronym a lot.
We do. And RMs have become pretty standard now in post-training for large language models, LLMs. Their main job basically is to capture, the paper calls it, nuanced and sophisticated human preferences.
So not just is this answer correct, but is this answer helpful or polite or safe, that kind of thing?
Precisely. They act like an internal critic for the AI, learning what counts as good or preferred based on feedback from humans, rather than just checking against, say, a database of facts.
That sounds incredibly important, but I gather they've been a bit tricky. Brittle, maybe? What's the main hurdle?
Yeah, brittle is a good word for it. The core issue, according to this research, is that many of the current, even state-of-the-art OpenRMs just perform poorly on evaluation benchmarks.
Why is that?
Well, the paper's hypothesis is that this brittleness, it mostly stems from limitations in the preference datasets used to train them.
Ah, the data itself.
Exactly. These datasets are often narrowly scoped. They don't cover enough variety. Or they might be synthetically labeled, meaning another AI generated the labels, not a human.
I see. Or just not checked properly.
Right. Or they just lack rigorous quality control. It's like trying to teach someone gourmet cooking using only microwave meal examples. The input quality limits the output.
Okay, so it's easy enough to tell an AI if a math answer is right or wrong. That's objective.
Correct. Simple, rule-based rewards work fine for things like math or code verification. You have a clear ground truth.
But that approach just falls apart for preferences, right? For subjective stuff.
Completely. Those rules just can't capture complex human preferences. And that's exactly why effective RMs are so vital. They're what pushes AI beyond simple correctness towards genuine human alignment.
And it sounds like even the tests they were using, the benchmarks, weren't quite hitting the mark either. Like, getting a high score didn't mean the AI was actually better.
That's another fascinating point. Existing benchmarks, like the older reward bench, apparently led to potential over-optimization.
Meaning gaming the test.
Sort of, yeah. Scores on those benchmarks often showed weak or even inverse correlations with how the models actually performed in real-world tasks downstream.
Inverse. So doing better on the tests sometimes meant doing worse in reality.
That's what the data suggested. It's a huge blind spot, right? It really showed they weren't measuring genuine progress in capturing human preferences effectively.
Wow. Okay, so that really underscores the need for a better approach, which brings us to Skywork AI. How did they tackle this challenge? What's their big idea?
Their main focus was squarely on enhancing the data quality of existing preference data. It wasn't just about more data, but better data.
And they built this huge new data set to do it.
They did. It's called SimPref 40M, massive scale, 40 million preference pairs.
40 million, okay.
But again, the scale isn't the only story. It's how they curated it. That's where the innovation lies.
Right, this human AI synergistic two-stage pipeline they talk about. Let's break that down. Stage 1 sounds like it's all about quality control with humans involved.
Exactly. Stage 1 is small-scale, meticulous, human-in-the-loop curation. You have humans providing verified annotations under a stringent protocol for quality assurance.
Okay, so real people making careful judgments.
Yes, but alongside that, you also have LLMs being used for automatic curation based on human guidance. They act as LLM judges, guided by the human input.
So it's not purely human, not purely AI, it's a collaboration.
Precisely. And it's iterative. They first train a reward model on what they call silver data. That's the stuff verified by the LLM judges.
Silver data, okay.
Then they test that RM against the gold data, the human-verified stuff, to see where it's weak.
Finding the gaps in its understanding.
Right. And then, cleverly, an adaptive retrieval mechanism pulls out more samples similar to those where the RM struggled.
And those difficult samples go back to the humans.
Exactly. They get re-annotated by humans to specifically target and fix the RM's weaknesses. It's a continuous improvement cycle.
And the human protocol itself sounds really rigorous. They're not just clicking yes or no, are they?
Not at all. It's quite detailed. Annotators can use external tools, search engines, even other advanced LLMs to help inform their judgment.
Okay, so they can research.
They can research, but, and this is a key point, full reliance on LLMs for labeling is strictly prohibited. The human judgment remains central.
That makes sense. Keeps the gold standard truly human.
And they also use these specific preference attributes like the task type, how objective it is, if it's controversial, to make sure the annotations are diverse and follow clear guidelines.
So stage 1 sets this high-quality foundation. Then stage 2 is where they achieve that massive scale.
Correct. Stage 2 is the large-scale automatic curation. This is where they scale up to tens of millions of in-the-wild preference data pairs, but crucially, without direct human supervision on every single pair.
How do they maintain quality, then, without humans looking at everything?
They use the best RM trained in stage 1, along with a special gold reward model, one trained only on the human-verified data as filters.
Ah, so they use the models trained on the best data to judge the rest.
Yes, using consistency-based filtering strategies to essentially approximate what true human preference would look like at scale.
And this is where that really interesting recycling idea comes in, right? Using the data that was initially thrown out.
Yes. This was genuinely fascinating. They experimented with recycling data initially filtered out as low quality by simply flipping the chosen rejected order. So if the model initially preferred response A over B and that pair was discarded, they tried treating it as if B was preferred over A.
That sounds counterintuitive. Did it work?
Amazingly, yes. It led to consistent performance gains. It suggests the filtering process was not only finding good data, but also identifying bad patterns. And by inverting them, they could actually extract useful signal.
That's wild, turning trash into treasure almost. It really changes how you think about data collection.
It absolutely does. It implies even bad examples contain valuable information if you know how to look at them.
Okay, so this whole meticulous two-stage human-AI synergistic process, did it actually deliver? What about the performance of the final reward models?
Well, this is where it gets really impressive. They released the Skywork-Reward-V2 series, 8 models, ranging from a pretty small 0.6 billion parameters up to 8 billion.
So not enormous models by today's standards.
Not compared to the giants, no. And these were trained on a curated subset of about 26 million preference pairs from that big SynPref 40M dataset.
And the results, how did they stack up?
They achieved state-of-the-art performance across 7 major reward model benchmarks. That's quite a claim.
State-of-the-art across the board, basically.
Pretty much. Let's look at general human preferences first. Their models outperform not only much larger ones, including 70 billion parameter models.
70 billion, wow.
But also this emerging class of generative reward models, which are a whole different approach.
So better than bigger and better than newer types, too.
And get this. Even at a scale of 1.7B parameters, a reward model can outperform a 70B model on all benchmarks except for Reward Bench and Reward Bench V2.
Hold on, a 1.7 billion parameter model beating a 70 billion one.
On most key benchmarks, yes.
That completely flips the script, doesn't it? The idea that bigger is always better.
It massively challenges that assumption. It strongly suggests that data quality can significantly bridge that model size gap. Meticulous curation might be more important than just raw parameter count.
Incredible. Okay, what about objective stuff, like math or coding accuracy? Can these smaller models still compete there?
They hold up really well. On benchmarks like Judge Bench and PPE correctness, which test factual accuracy, their 3P model achieves math performance equivalent to O3 Mini High, a known strong performer.
And the bigger one, the 8B.
The 8B variant actually outperforms O3 Mini High in math, So yes, they're top tier even on objective correctness.
Okay. And you mentioned best of n scaling. What does that tell us?
Right, best of n, or BON. Imagine the AI gives you, say, 5 possible answers. BON measures how the reward model picks the single best one out of that set.
Selecting the top choice. Crucial for usefulness.
Very. And they show strong BON capability in both helpfulness and harmlessness. All 8 of their RMs outperformed GPT-4o, which was a previous SOTA,
OpenAI's latest,
by up to 20 points on one benchmark, RMB. That's a really significant margin in picking the best response.
And what about biases? Can these models see past superficial style differences?
That's tested by RMBench. And here, too, the Skywork models outperform all baselines. Crucially, they show much smaller performance differences between easy and hard examples. It suggests they have more de-biased representations of preferences. They're less easily fooled by fancy writing or specific phrasing, focusing more on the actual substance and intent.
That's really important for fairness and reliability. What about the really tough stuff, like following complex instructions precisely?
Yeah, that's often a weak point. On RewardBench-V2, which tests things like precise instruction following, most existing RMs apparently score below 50%.
Pretty low.
Very. But the Skywork-Reward-V2 models, especially the 8B one, outperform strong proprietary models like Claude 3.7 Sonnet and Gemini 2.5 Flash Preview.
So better than some of the big closed models on these complex tasks.
In this specific capability, yes. It really highlights how effective that careful data curation was for teaching nuanced understanding.
The proof seems overwhelming, but the paper also includes ablation studies, right? Where they take things away to see what really matters.
Exactly. And these are often the most revealing parts of AI research papers. They really let you pinpoint why something works.
So what did they find? Did it confirm this quality over quantity idea?
Absolutely. Unequivocally. Yeah. They showed that just increasing the amount of uncurated data gave minimal performance gains. Barely moved the needle.
So just hoovering up more random data doesn't help much.
Right. But with curated data, we observe consistent performance improvements as more data is added. The quality unlocked the benefit of quantity.
That's such a critical finding for anyone training these models. Don't just add data, add good data.
Precisely. And remember that recycling trick?
Flipping the chosen rejected pairs?
Yes. The Ablation study confirmed that doing this with the discarded data led to consistent performance gains.
So it wasn't a fluke?
No. It proves their curation process didn't just select good data. It also identified bad patterns so effectively that even the inverse of that bad data was useful for training. It implies a deep understanding of preference structure.
And then there's the point about how little curated data was needed for a big impact.
This one's staggering. Using only 1.8%, that's roughly 290,000 samples, of the full training set surpasses the previous state-of-the-art, a 70B model, at the 8B scale.
Just 1.8% of their curated data was enough to beat a massive model.
Yes, it's probably the single most powerful demonstration of the impact of high-quality, well-curated data in the entire paper.
Mind-blowing. It really emphasizes efficiency and the power of careful work over brute force.
Completely.
And throughout all this AI-assisted curation, how important did the human element turn out to be in these studies?
Absolutely critical. The Ablation showed that simple LLM curation, just using an AI judge without the rigorous human loop, barely improves RM quality.
Yeah.
Only by 0.1 points. It's almost noise.
So AI judging alone isn't enough?
Not even close. In contrast, human curation is crucial to data quality. It yielded the single largest improvement, 2.3 points over the baseline. The human touch was essential.
It really shows that human insight is still irreplaceable, doesn't it?
It does. Especially for setting that initial gold standard and handling the nuanced, tricky cases.
And even how the humans did their curation mattered.
Yes. Providing them with those LLM-generated preference attributes to consider, and having them follow the full annotation protocol, including using external tools.
To search engines, other AIs.
Right. That combination boosted quality significantly further, adding up to a 3.2-point improvement over just basic annotation. It really underlines the synergy aspect. Humans empowered by AI tools, following a rigorous process.
Wow. So let's recap. We've really uncovered that the secret sauce for training AI that truly gets human preferences isn't just more data or bigger models. It's this meticulous curation, this high-quality data that comes from a real dance between human intelligence and AI's ability to scale.
That's the core takeaway. And for you listening, you now have a much deeper grasp of these cutting-edge methods making AI more helpful, safer, and crucially, better aligned with what we actually want. This deep dive really shows reward models acting as that vital AI compass.
Which leads to a final thought to leave you with. Given that these reward models are becoming, as the paper suggests, potentially the most, if not the only, critical components guiding AI, guiding them through complexity, aligning them with our values, helping them evolve, what new questions does this raise?
That's a big one.
As these systems get an increasingly sophisticated but still learned understanding of what we think is good based on data we curate, what new ethical considerations pop up?
Right. And how might refining these models, which are essentially learning mirrors of our own stated preferences, start to subtly change our own understanding of what it means to be well-informed or aligned, especially when we interact so much with these aligned systems?
A fascinating, maybe slightly recursive thought to ponder.